Hello everyone, my name is Siram Reddy Saipon. Today I am presenting my Embedded Systems Internship Project Electric Vehicle ADAS dashboard using STM32 Bluepill and Python. The objective of this project was to simulate an electric vehicle dashboard with advanced driver assistance system features using STM32 firmware, UART communication, PICSimLab simulation, and a real-time Python dashboard. During this internship, I learned embedded system C programming, STM32 peripheral configuration, UART communication, firmware development, debugging, and desktop application integration. This project was completed as part of my internship conducted by EMERTXE. The internship focused on embedded systems development using STM32 microcontrollers. During the internship, I worked on developing firmware integrating UART communication, creating a Python dashboard, and validating the complete system using PICSimLab. The project followed a complete workflow from the firmware development to software visualization. Developing embedded automotive applications normally requires expensive hardware and real vehicle electronics. For students and beginners, testing dashboard applications become difficult because real hardware is costly and not always available. The main goal of the project was to develop a low-cost simulation platform where EV parameters and ADAS functions can be tested completely in software. The objectives of this project were to simulate important electric vehicle parameters, to develop firmware using STM32 Hall libraries, to establish UART communication, to build a Python based dashboard, to simulate ADAS features, to monitor all vehicle parameters in real time. This slide explains the complete system architecture. On the left side, potentiometers simulate vehicle inputs such as accelerator and brake. These analog signals are read by the STM32 label through its ADC. The firmware processes these values and calculates vehicle parameters like speed, battery, state of charge, motor temperature, torque, and range. The ADAS module then evaluates the simulated surroundings and calculates safely parameters such as time to collision and warning states. Finally, the processed data is transmitted over UART to Python dashboard where it is displayed graphically for the user. The hardware used in the project includes STM32F103C826 Bluepill, potentiometers for analog input, HCSR04 ultrasonic sensors in the simulation, UART communication, PC running the dashboard, PICSimLab for virtual hardware simulation. The software tools used include STM32CubeIDE for firmware development, PICSimLab for hardware simulation, Python for dashboard development, VSPE for virtual serial communication, EmbeddedC programming language, STM32 HAL libraries for peripheral control. The firmware starts by initializing all peripherals including ADC, timers, GPIO inputs, and UART. Inside the main loop, the firmware continuously reads sensor values, calculates EV parameters, updates ADAS logic from its UART package, and sends them to the dashboard. Timers are used to maintain a stable update rate. This module calculates the important EV parameters. These include vehicle speed, battery state of charge, motor temperature, motor torque, remaining range, accelerator percentage, brake percentage. All these values are continuously updated and transmitted to the dashboard. The ADAS module provides basic driver assistance feature. It includes front collision warning, blind spot detection, time to collision calculation, alarm generation, bird eye visualization. These features help demonstrate how modern driver assistance systems process vehicle surroundings. The STM32 communicates with the Python dashboard using UART communication at 115200 baud rate. The firmware sends structured ASCII packets containing speed, battery, temperature, torque, range, and ADAS information. The Python application receives these packets and processes them and updates the dashboard in real time. This is the Python dashboard during the internship, which was developed during the internship. It displays speedometer, battery level, live speed graph, EV matrices, bird eye ADAS view, alarm status. The dashboard updates continuously based on the data received from STM32. PICSimLab was used to simulate the STM32 Blue Pill hardware. It provides virtual potentiometers, ultrasonic sensors, and virtual terminal. This allows testing of the firmware without requiring physical hardware. Now I will demonstrate the complete working system for a while. This is the my STM32 CubeID project. The firmware is written in EmbeddedC using STM32 HAL libraries. The project contains separate modules for EV control, ADAS, UART communication, and ultrasonic sensors. These are the main files, not all files, but EV control.c, control.h, ultrasonic.c, h, and our main heart of the project or IOC. So IOC, what we have used. So the project compiled successfully without any errors. Here we can see the UART packets transmitted by the STM32 firmware. These packets contain the EV matrices and ADAS informations. This is the blue pill. We can load the bin file. Already it have been loaded before. Um, this dashboard receives the UART packets and visualizes the data in real time. The speedometer, battery indicator, speed graph, EV matrices, and ADAS bird eye view update continuously based on the STM32 firmware. I will show you by changing the potentiometers. Through that, you can see the live demo of changing the dashboard values. This increases the acceleration. Can change the acceleration. This is the brake. This is the battery percentage. This is the temperature. Okay. So the project successfully demonstrates end-to-end integration between embedded firmware simulation, UART communication, and a desktop dashboard. The complete system operates in real time. Some of the challenges I faced included UART synchronization, PICSimLab configuration, dashboard integration, and debugging communication issues. These challenges improved my debugging and problem solving skills. Through this internship, I learned STM32 HAL programming, embedded C, UART communication, Python GUI development, simulation techniques, system integration, embedded debugging. In future, this project can be enhanced by integrating real HCSR04 sensors, CAN communication, GPS, Bluetooth connectivity, cloud monitoring, machine learning based data. So, I successfully developed a real-time electric vehicle dashboard and data simulation using STM32 Bluepill, PICSimLab, and Python. These are the outputs. These projects demonstrate embedded firmware development and serial communication and graphical visualization in a complete embedded system. So, thank you for your time and attention. I hope you enjoyed the presentation. If you have any questions, I'm also happy to answer any questions. You can Uh, you can type in comments or in our announcements page.